In this lecture, we're going to talk about maximum and minimum values of a two-variable function fxy over some subset R of the plane, and this R is called a region. So look at this picture, and we see that to be at a maximum, these peaks, these black star peaks, you have to be a maximum from every single direction. Regardless of how you're approaching this peak, you have to go up to the peak and then immediately afterwards, fall down. And by symmetry, exactly the same thing is for these green star valleys. So the idea to try to find a minimum for f at AB is to create a one-dimensional function, t2f pq of t, which is f at this potential maximum point plus a small perturbation in the direction pq. So pq here is unit direction vector. So for every direction pq, we do this. So we take f of a plus pt, b plus qt, and we look at that at 0 for every single direction. And so that should give us a critical point at 0 for every single direction. And we could check for that. And we could then use the first derivative test around that for every single direction. Well, this sounds rather impractical, and it is, but it becomes somewhat more practical if we recall our result that directional derivatives are obtained from the gradient. So this becomes more practical when f is continuously differentiable around AB. And so then we could take the derivative of t of this new function f pq at t, and we could write that out as the gradient, so the partial derivative in f at this point times p plus the partial derivative in y at this point times q. And that simply then becomes the gradient of f at a plus pt, b plus qt times the unit direction vector pq. And so we would need a critical point for all directions at 0 for it to be possibly a maximum or a minimum. And now, since this has to be true for every single direction, we have the result that the gradient of f at AB must be 0. So we'd have a critical point in every single direction if and only if the gradient of f at AB is equal to 0. And we can interpret this more from a geometric point of view by considering the tangent plane of f at this point AB. So if we write out the general tangent plane equation, we have this small perturbation in z. So z minus fab has to be equal to the partial derivative in x at AB times x minus a plus the partial derivative in y of f at AB times y minus b. But if the gradient is 0, both these partial derivatives are 0, and the tangent plane just simply becomes z is equal to fab. In other words, the tangent plane is parallel to the xy plane at such points. The potential maximums and minimums are where the tangent plane is parallel to the xy plane. Now to go on, we want to set a little bit of notation. So we recall that a ball BAB delta is the set of xy such that the distance from AB to a point xy in the ball is less than delta. In other words, the square root of x minus a squared plus y minus b squared is less than delta. And that would be for any such delta. This generalizes the idea of an open interval to 2 or more dimensions. We have some other definitions that are going to be important in this course. A set E in R2 is said to be bounded if there is some positive m such that the magnitude of x is less than or equal to m for all x in E. 2. An x in R2 is said to be a boundary point of E if for any delta there is a y in E and a z in E complement such that the distance to y and the distance to z is less than delta. So in other words, the distance from x to E and x to E complement is less than delta. And delta is arbitrary. And so what that basically means is you have to be touching both sets. Beyond the boundary, you have to be touching both E and E complement. E is said to be closed if it contains its boundary points, and a closed and bounded set K in R2 is said to be compact. And compactness and bounded properties are very important. We can go on and define what we mean by maxima and minima. AB is a local maximum if FAB is greater than or equal to FXY for all XY in a ball around AB. The ball can be arbitrarily small, but in some ball. So this is basically saying that there's no other point higher than FAB around FAB. And around is interpreted very generally because it might be a very small area. AB is then a global maximum on D if FAB is greater than or equal to FXY for all XY in D. So you can have multiple global maximums. It just would mean that these points have the same value. So maybe the function is flat for a while and then tails off in the various directions. All the area where it is flat and at the highest point would be a global maximum. AB is a local minimum if it is locally less than or equal to all the values around it. So within some small ball of AB. And it's a global minimum if it's less than or equal to all values of the function applied at its domain. And collectively, maximum and minimum are referred to as extrema. There's a nice result from analysis that says any continuous function obtains its global extrema, both its maximum and minima, on a compact set. So when the region that we're trying to find the maxima, the global maxima on, is compact, we know that they exist. And so you couldn't have a possibility that there is no global maximum because it's heading off to higher and higher values on the boundary, because the boundary would be included and infinity would not. And so you couldn't be getting higher values as you headed off to infinity in some direction or headed off to the boundary of the region because they're excluded. Critical points and saddle points. So we have some generalization of critical points and inflection points like what we had in single variable calculus. So in particular, AB is said to be a critical point for F if either the partial derivative of F in X does not exist, or the partial derivative in Y does not exist, or else the gradient is equal to 0, the latter being motivated by our first observation above. Case 3 will be referred to as smooth critical points, where the gradient exists and it's equal to 0. And so Fermat's theorem says that if AB is an interior point in R and an extremum, local maximum or minima, then AB must be a critical point. And that just comes from the first derivative test from first calculus and the work we did above, that you need a critical point in every single direction, which would imply that the gradient is 0. So Fermat's theorem is only talking about interior points. So if the region R is compact, you still would have to look at the boundary points. You also have to test that there even are global extrema when either R is open, which could be like an open ball, but it also could be including points heading to infinity, or when there are singularities, i.e. vertical asymptotes in F. The next thing that we want to recall as an inflection point is a point of concavity change. A smooth critical point that is an inflection point in any direction is not an extrema. There is no multidimensional version of an inflection point. The closest analog is a saddle point. A saddle point is a point in the domain of a function that is a smooth critical point but not a local extrema. And so we check to see if we have a saddle point. So the first case that you had a saddle point would be you had an inflection in some direction. Another check for a saddle point would be you have a maximum in some directions and minimums in others. And a third one is there is a concavity up in some directions and concavity down in other directions. In any of these cases, you have a saddle point. So here is an example of a saddle point where you can see that at that point, it's a minimum in some directions and a maximum in others. But in every case, it's a critical point because of the fact that it's smooth and the tangent plane at that point is parallel to the xy axis. And so we're now ready to give our tests for whether we have local extrema, and they mirror single variable tests. The first derivative test, unfortunately, is harder to use than in single variable calculus, but here's how you would use it. You first form all of the scalar test functions, f p q of t, which is equal to f a plus pt, b plus qt, where p, q is a unit direction vector. And so now with this function, we can just do a scalar test in every single direction. So in particular, we will look at the first derivative of fpq of t and check what happens as t goes from below up to 0 and then through 0 into the positive numbers. And we'll classify the extrema at 0 according to this table. So if the derivative goes from a positive value from below 0 to a negative value, then you had a maximum of fpq at 0. If it went from a negative value for t less than 0 to a positive value at t above 0, then you had a minimum. If it didn't change sign, it's not an extremum. It's a possible inflection point. And you can do this for every single direction. The problem is you have to check every single direction, which can be difficult for some problems, and it can be time consuming. And you have to look at this first derivative around 0 for every single direction. And this is why the first derivative test is so more powerful than the second derivative test, but it's often not used in favor of the second derivative test, just because the second derivative test generalizes easier to multivariable situations. The second derivative local test is along any direction, you take the second derivative of these same functions, f pq, where pq is a unit direction vector, and look at that at 0. And we can again classify the extrema according to this value of the second derivative. So you'd still need to have a critical point, so you'd still need the gradient of f to be 0 at AB, and then you form these functions and you look at the concavity in each of these directions. If the second derivative has negative value, then you have downward concavity, and that would mean it's a maximum. If the second derivative of 0 of this function was positive, it would mean you'd have a minimum. If it's 0, it means the test doesn't apply. If it's undefined, it means the test doesn't apply. So the advantage of this test is you only have to test the second derivative at 0 instead of the first derivative around 0, which is a big difference because you have to look at every direction. The disadvantage is it's less powerful than the first derivative test, just like the single variable case. Moving forward with the second derivative test, we recall the Hessian of a twice differentiable function of f is the Hessian of f at xy is the product of the normal second partial derivatives minus the product of the two mixed partial derivatives. Now remember that if we could show that either of these mixed partial derivatives is continuous around xy, then these have the same value, and then we just have that value squared. So the second derivative test is suppose that the second partial derivatives exist and that we have the continuity of this mixed partial, so that they're both the same. So they exist and they're continuous in an open ball containing the critical point xc, yc, which we determine by looking at the gradient. Then a local minimum exists at C if the Hessian is greater than 0 and the first normal partial derivative or the first normal partial derivative is greater than 0. And a local maximum exists at this critical point if the Hessian is greater than 0 and one of the normal second partial derivatives is less than 0. It's a saddle point at C if the Hessian is less than 0. In this case, C can be neither a maximum nor a minimum, and the test is inconclusive if the Hessian is 0. So we finally have the global test for a maximum. Suppose that D is compact. Evaluate the local maximum or critical points if limited number within D. Find the maximum on the boundary. The largest values from step 1 and step 2 will be the global maximum. Of course, you might not even have a global maximum if D is not compact, i.e. it's either partially open and or infinite in some direction. Thank you.